Hello and welcome to this video on the fundamental theorem of line integrals on curved manifolds using differential forms. Alright, so in the setting of differential geometry, the fundamental theorem of line integrals generalizes the classical result from vector calculus to curved manifolds by using the machinery of differential forms. This theorem states that the integral of an exact one form along a curve depends only on the values of its potential function at the endpoints. All right, so let's make a start. So in Rn, the classical form of the theorem, in Rn, the fundamental theorem states that a vector field f is the gradient of a scale function small f, so f is del or nabla of f. Then for any smooth curve gamma from the closed interval ab to Rn, the line integral of f along gamma satisfies the integral of f dot dr along gamma is f of gamma of b minus f of gamma of a. So the difference of the function, the potential function f evaluated at the endpoints a and b on the curve gamma of b, gamma of a. That's along the curve. So for example, in R3, if we let f be x squared plus y squared plus z squared, then del f is 2x, 2y, 2z, the gradient vector. And we consider the helix gamma of t is cos t, x component, y component sine t, z component t, and we consider it on the interval of, might help if I hide that, 0 to pi, because we're going to take the variable t from 0 to pi. So the tangent of velocity vector then is d dt of this, so the derivative with respect to the parameter t. We're going to have in the x component there minus sine t, x dot component, cos t for the y dot component, and 1 for the z dot component. All right, so as a picture here in R3, here's our curve gamma of t. All right, we see it's a mapping from the interval AB on R to R3. All right, so that's our mapping. Substituting gamma of t into f of x, y, z, so we want f composed of gamma, and f is x squared plus y squared plus z squared. Well, then f composed of gamma is f of gamma of t, and the x component of gamma, cos t, goes in here. The y component of gamma, sine t, goes in here, and the z component gamma of t goes in here. Okay, so z squared becomes just t squared. X squared is cos t squared, y squared is sine t squared. Okay, now we can leave it in that form or simplify it down. F of gamma of t then becomes a scalar function 1 plus t squared. All right, so evaluating f of gamma of t at the endpoints, well, gamma of t equals 0, putting t equals cos of 0 is 1, sine of 0 is 0, and substituting t equals 0 into t, we get 0 here, so we get 1, and at the other endpoint, gamma of pi, similar thing here. Okay, we get cos of pi is minus 1 square, and then t equals pi up here, so we get pi squared. So we get 1 plus pi squared. The integral along gamma of f dot dr, which was del f dot dr, is then just the difference between the endpoints according to the fundamental theorem of line integrals. So it becomes the potential function f evaluated at gamma of pi and f evaluated at gamma of 0, the two endpoints we're interested in. That's 1 plus pi squared minus 1 is pi squared. Okay, that's our curve there. So the differential dr represents the tangent or velocity vector, and I'll show you that in the next slide, along the curve gamma of t, written in differential form notation as dr, r bold being the vector r, is gamma dash of t dt, and that comes from the derivative of the vector r with respect to t is d dt. Gamma of t is gamma dash of t, and I showed you what that was before. That was the minus sine t, cos t, and 1 we saw on the previous slide. Next slide over. So we want to find the integral of f dot dr along gamma is the integral del f dot dr along gamma. So del f dot dr is that, the gradient vector dotted with the dr vector, and dr is this vector here, dr tangent to the curve at each point is gamma dash of t dt, all points t along here. Evaluating this scalar product, we get minus 2 cos t sine t plus 2 sine t cos t, so they cancel out. We're left with just plus 2t dt. Okay, and then evaluating that between t equals 0 and pi, t equals 0 and pi, the endpoints, we get the antiderivative of 2t is t squared, evaluated then, so the exact integral then becomes evaluated between 0 and pi, gives us pi squared, and that confirms the equality that the integral f dot dr along gamma is just simply the potential function evaluated at the endpoints of the curve, the difference between those two endpoints. All right, so let's go now to the curve manifold case. So let M be a smooth n-dimensional differentiable manifold, and let omega be a smooth exact one form on M. That is, there exists a smooth function f that maps M to R such that omega is df. Given a smooth curve gamma that maps the interval AB to M, we define the line integral of omega along gamma as the integral of omega along gamma is the integral A to B of the pullback of omega under gamma. And that gamma is our curve, our smooth curve. So we're going to pull back the one form omega along the curve, pull it back along the curve there. And so the integral of omega along the curve is then equal to the integral between the endpoints AB of the pullback of omega under gamma. So the pullback gamma asterisk omega is a one form on AB, which can be expressed in terms of the parameter t. So the pullback of omega becomes omega composed of gamma of t, d gamma dt dt. All right. Looking at this, here's our manifold M. Here's a local coordinate system within it, so we'll talk in terms of that because no one coordinate system covers the whole manifold. We have a curve in that region in our local coordinate patch here, in which we can use the coordinates x1, x2 to xn. Gamma of t is our curve. It's a map from the reals here, from that closed interval AB. So that's a starting point, end point. Gamma is the map from the interval AB to M. All right. Now, if we have some function f in our coordinate chart here, f contained in M is a map from U to R, and f composed of gamma, by the same token, pulling f back along gamma, okay, is the same. F composed of gamma is from the closed interval, I meant closed interval there, not open interval, AB to R. Okay, same thing, both takes us the same way. So that's where we stand. By substituting omega as df, we obtain, sorry, our one form will be df, the differential of the scalar function f, or the zero form f. So the pullback of df under gamma is, as we found in other videos, is the exterior derivative, or the derivative of total derivative f composed of gamma. This is because the exterior derivative commutes with the pullback. And to show this in R3, let's say gamma of t is x of t, y of t, z of t. And the composition f composed of gamma, f composed of is then f of x of t, y of t, z of t. So it's a function of t. The differential one form of f is df partial f on partial x dx plus partial f partial y dy plus partial f partial z dz. And by definition of pullback, gamma star acts on the differentials dx, dy, dz by substituting the expressions from gamma of t. So the pullback of dx under gamma is dx dt times dt. Same for the pullback of dy under gamma. Same for the pullback of dz under gamma, dz dt dt. So applying this to df here, we get the pullback of df under gamma is df dx, partial f times dx dt times dt, partial f partial y times dy dt dt, and so on here. Okay. Next step then, factor out dt, and the pullback of df under gamma is then this object here times dt. So the function f composed of gamma is a function of t, as we can see. So its differential is, the differential f composed of gamma is d dt f of, remember it's f composed of gamma, so it's f of x of t, y of t, z of t, as we saw earlier. So using the chain rule, d dt of that becomes partial f partial x times dx dt plus partial f partial y times dy dt plus so on. And so the differential of total differential exterior derivative of f gamma is this object here, the dt on the end. All right, but that looks familiar because we've already found that up here. So that gives us the desired result that gamma, the pullback of df under gamma, is equal to the derivative differential exterior derivative f composed of gamma. So this result expresses the compatibility of differentiation with pullbacks. The pullback gamma star is simply restricting df to the curve gamma, which should be equivalent to differentiating f after substitution. All right, so again, here's our manifold here. Here's a point P on the interval AB, which is mapped to U in M. Okay, our local coordinate chart. At that point P, we have the map gamma of P. Okay, now at that point, we have the cotangent space to U at the point gamma of P here. Okay, and we have our one form df. Okay, we're going to then pull that back under gamma, and the pullback of df under gamma is this one form over here. All right. So that's what's happening in terms of cotangent spaces. So the cotangent space to R here at the point P is just R. All right, we can go a bit further here because f composed of gamma is the pullback of f under gamma. And that means that the pullback of df under gamma is the exterior derivative of f composed of gamma, which is the exterior derivative of the pullback of f under gamma. All right. And so in particular, we found that the pullback of df under gamma is the exterior derivative of the pullback of f under gamma. They commute. So the result expresses the fundamental fact that differentiation commutes with pullbacks. It means that pulling back a differential one form is the same as first pulling back the function and then differentiating. So this property generalizes to higher degree differential forms as well, and that'll be the subject of the next video. So the pullback of d omega under gamma is the pullback of omega under gamma and then the exterior derivative of the lot for any k form omega, but that's the subject of the next video. Anyway, since the exterior derivative commutes with pullbacks, we integrate. So the integral of df along gamma is the integral of pullback of df under gamma between the intervals a to b. All right, because remember it took it back on, remember we pulled it back from here, the cotangent space to this point here, pulled it back to the original value here on r. And so it's an integral of one variable, dt. All right. And hence the intervals a to b. All right. But that's also equal to the integral of the exterior derivative of f composed of gamma, which is a scalar function of the single variable t, if you remember from earlier in our examples here. All right, since the exterior derivative of f composed of gamma is d dt, f of gamma of t dt, we apply the fundamental theorem of calculus, and the integral a to b of d dt of that with respect to t is f of gamma of b minus f of gamma of a. Hence, we obtain the fundamental theorem of line integrals on a manifold. The integral of omega along gamma is simply the integral of the potential function of value a between gamma of b and gamma of a. All right, the interpretation is implications. So the integral of an exact one form omega equals df along any curve depends only on the endpoints. This means that the integral is path independent if the domain is simply connected. We talked about simple connection and contractibility in the previous video to this one. So you look at that on the playlist. If omega is closed, i.e. d omega, and again, all this was the subject of the last video, d omega equals 0, then it is locally exact in a contractible region. Again, all of that was covered in the last video. This is a generalization of conservative vector fields from classical calculus, and again, see the last video for that. So let's have an example of the fundamental theorem of line integrals on the two-sphere, S2. So consider the unit sphere S2 with standard spherical coordinates, theta, phi, and a metric given by this. Let's just take, for argument's sake, our one form to be omega is cos theta d phi. And to check if omega is exact, we compute its exterior derivative. And we see d omega is d cos theta d phi is minus sine theta d theta wedged d phi. All right, since d omega does not equal 0, the form is not exact globally on S2, which is expected since S2 is not contractible, because think about what happens to phi at the poles. What value does it take? However, if we restrict to a region excluding the poles, then we can define a potential function f such that df is cos theta d omega. On such a region, the integral along any path gamma from theta 1 phi 1 to theta 2 phi 2 is the integral of omega along gamma is simply the difference between the potential function evaluated at the endpoints. That's this f evaluated between the endpoints. And this demonstrates the fundamental theorem on a curved space. Now let's work through an example of the fundamental theorem of line integrals in Schwarzschild spacetime using the differential forms. All right, so in Schwarzschild coordinates, we have CTR theta phi. The metric is this object here. All right, and we'll use the Schwarzschild time t as a parameter along the curve. So let's consider a simple function f of r equals the natural log of r. No particular reason for choosing this one. It's simply convenient as an example because its derivative doesn't just disappear, become zero or anything, as you'll see in a moment. No particular reason for choosing it otherwise, all right? Just simply for an argument's sake, for demonstration purposes only. So its differential one form of df is 1 on r dr. Okay, if I just chosen f of r equals r, I would have got a constant here or something, okay? So it was easy to choose the natural log of r. Let's consider a world line gamma in Schwarzschild space-time. So that's the point of this argument here. So let's take a radial time-like geodesic. For non-spinning black holes, you can have purely radial motion. You can't have that with the spinning black holes. That's not possible because of frame dragging. So let's take a radial time-like geodesic that's falling directly into the black hole. So it could be an observer or a particle with mass. And the geodesic will be parameterized according to the proper time as measured by the falling observer using their own wristwatch or timing device they carry with them. Same with the particle. So gamma of t will be ct of tau. Tau is proper time, r of tau, and then theta 0, phi 0 are constants because it's going to be purely radial motion. All right, where theta are constants, so the motion is purely in the CTR plane. The tangent vector of this world line, gamma dot, is d gamma d tau, is ct dash partial t, the basis vector in the t direction, plus r dot times the basis vector in the r direction. Don't forget that the t dot there is dt d tau. All right. Next, we want to pull df back along gamma. So the pullback, remember when we integrate, it's easy. We use the pullbacks because we take something that's on a manifold that's complicated to integrate, and when we pull it back, as we do in these examples, back to the real number line, it becomes very simple to integrate. This is where the pullbacks are used with the integration. But there's a whole series on the pullbacks in this playlist, so please go and have a look at that. Okay, back to the job now. So the pullback along the curve, under the curve gamma of t, which is parameterized by proper time tau, replaces dr with the derivative of r along the curve. So the pullback of dr under gamma is dr d tau times d tau is r dot. Dr d tau is r dot d tau. Okay, dr d tau is r dot. Similarly for the time variable. Since the motion is purely radial, the pullback of df along gamma is the pullback of 1 on r dr. Remember, df was 1 on r dr under gamma, which is 1 on r tau. Remember, r is parameterized in terms of tau, times r dot of tau, d tau. All right. Okay, next we apply the fundamental theorem of line integrals. So the integral of df along gamma is the integral of this between tau 1 and tau 2. Since dr is r dot d tau, remember dr d tau is r dot of tau, this integral simply simplifies directly to the integral between tau 1 and tau 2 of 1 on r dr is the natural log of r evaluated between tau 1 and tau 2. Here we go. And hence the integral of df along gamma is f of gamma of tau 2, minus f of gamma of tau 1. And this result shows that just as in Euclidean space, the integral of an exact one-form df along a curve only depends on the function values at the endpoints. And this confirms that in Schwarzschild spacetime, the fundamental theorem of line integrals still holds when expressed using differential forms. Summary. So the fundamental theorem of line integrals on a manifold states that the integral of an exact one-form df along a curve depends only on the endpoints. The exterior derivative ensures the independence of path if the space is simply connected. And this generalizes the conservative vector field theorem from Euclidean space. And on non-contractible spaces like S2, remember the poles again, global exactness may fail, because remember, you're unlikely on a curved manifold to have one coordinate system to cover the entire manifold. So global exactness can fail, and it does with S2 at the poles, because what values does phi take? Theta is defined at the poles, theta is 0 and theta is pi, but what value does phi take? It has a Muthel angle. But local versions still hold. So you can still have on a local coordinate system, like I did earlier with you, where it holds, but not globally. Okay, where these results hold, because you don't have one coordinate system to cover an entire curved manifold in general. All right, I think that's it. Thank you very much for watching. No, there was no more. That's it. Thank you very much for watching. I hope you found this video useful. I'll see you in the next video. And until then, everybody, take care, and I look forward to seeing the next one. Oh, if you will, please push the like button and subscribe, if you will. That would help me greatly. I shall see you in the next video. Take care, everyone. All right, bye.